Hey everybody, and welcome to this video on simplifying radicals. So let's get this show on the road. Alright, consider the square root of 20. Now, with that 20 inside of that radical, it's very tied up in there. It's almost as if it's kind of blocked off, and we don't really have the ability to do much with it because it's confined within that square root. And in general, we'd like to have as little as possible within our square roots. So my question is, how can we change the square root of 20 so that it's the same, but with as little as possible within that radical? Well, what we're going to do is we're going to write the square root of 20 as a product of two other square roots. Now we have some options here. We can write it as the square root of 2 times the square root of 10, or we can write it as the square root of 4 times the square root of 5. Now, I would much prefer to write it as the square root of 4 times the square root of 5. Can you guess why? Because the square root of 4, that's a nice number. The square root of 4 is 2. So we can write this as 2 times the square root of 5. And note that what we've done now is we've taken the square root of 20 and we've rewritten it as something else that's the exact same thing, but with much less inside of that radical. And we call this the simplified version of the square root of 20. On a side note, when you have an integer and a radical, we almost always write these integer times radical, as opposed to the radical times an integer. For instance, while this may be a true statement, we wouldn't necessarily want to write this as the square root of 5 times 2. Even when I said it out loud, it was a little ambiguous. Is it the square root of 5 times 2? Is it the square root of 5 times 2? And you can imagine that if you were writing this, it would be possible for someone to make a mistake and think that that 2 was underneath the radical. And that's why this form is the one we generally use, and we don't write it the other way. Let's try another. How about the square root of 45? Now we want to simplify this expression, which means we need to write something that's exactly the same as the square root of 45, but with as little in the radical as possible. And we're going to go about doing this by kind of factoring this and writing this as the product of two square roots. Again, we've got some options. We can write it as the square root of 3 times the square root of 15, or we can write it as the square root of 9 times the square root of 5. And perhaps you can already tell which one of these I strongly prefer. I strongly prefer to write it as the square root of 9 times the square root of 5, because the square root of 9 is 3. And so we end up with a new way of writing the square root of 45, namely 3 times the square root of 5, which is of course equal to the square root of 45, but it's been simplified because now we have much less inside of our radical. And so in general, the strategy is going to be to factor the radical into numbers that are perfect squares, so that they will simplify, leaving as small a number inside of the radical as possible. This means that it's always going to be important to keep our perfect squares in mind when finding the factors of the radicand. In fact, it might even be easier to cycle through the perfect squares and see if they're factors of that radicand, instead of finding all the factors and seeing if they're perfect squares. And here's another example to highlight just that. Alright, now let's try simplifying the square root of 48. And now I have the perfect squares right here on the screen so we can reference them easily. Now we've got a whole bunch of different options for how to factor the square root of 48. Alright, so of these four options, which do you think is going to be the most efficient to help us find the simplified version of the square root of 48? Well, which of these four factorizations actually have perfect squares in them? And two of them actually do. One has the square root of 4, and we know that the square root of 4 is 2, but one has the square root of 16, and the square root of 16 is 4. So this factorization is actually going to be the most efficient. We can rewrite the square root of 16 as 4, and we end up with 4 root 3 as the simplified version of the square root of 48. Now the question is, were these other ones wrong? Not at all. Take a look. In this factorization, we do have a perfect square, namely 4. And we end up with 2 times the square root of 12. But my claim is, this isn't fully simplified yet. Why? Because we could factor 12 even further. 12 we can factor into the square root of 4 times the square root of 3. And so the square root of 4, that simplifies to 2. So we end up with 2 times the square root of 3. We end up with 4 times the square root of 3 again. We get the exact same simplified version. It just took us a few more steps. It might have not been quite as efficient. And in fact, for the outer two factorizations, both of those are going to yield us the exact same simplified version. It just might take us a little longer. For instance, all the way on the right, the square root of 6 and the square root of 8, neither of those are perfect squares. But we can factor each of them further. For instance, the square root of 6 is the square root of 2 times the square root of 3. And the square root of 8 we can write as the square root of 2 times the square root of 4. Now check it out. I see that we've got a square root of 2 and another square root of 2. And I know that the square root of 2 multiplied by the square root of 2 is 2. We also have the square root of 4. And 4 is a perfect square. Its square root is 2. And then we're left with the square root of 3. And so we end up with 2 times the square root of 3. We end up with the exact same simplified version. Last but not least, in our first factorization, neither of those are perfect squares, but we can factor the square root of 24 even more. We can factor the square root of 24 into the square root of 2 times the square root of 12. And check it out. We've got a square root of 2 and another square root of 2, and I know that these multiply to give us 2. So we've got 2 times the square root of 12. But I still think we can go further. I think we can factor the square root of 12 into the square root of 4 times the square root of 3. 4 is a perfect square, and its square root is 2. So we end up with 2 times the square root of 3, or 4 times the square root of 3, like we did in each other case. And so what I mean to say is, 1, it might be easier to cycle through the perfect squares and find the largest perfect square that's a factor of your radicand and use that factorization. Look how much easier it was using the square root of 3 times the square root of 16 than it was for any of the other ones. But also, it means if you don't feel comfortable finding that perfect square factor, it's okay. You can factor that radicand however you'd like. And if you keep on factoring and keep on factoring and keep on factoring, eventually you'll be able to simplify and you will get the same answer. A few more examples. Let's simplify the square root of 120. And we know we're going to factor this into two square roots whose radicands multiply to 120. But we prefer to find factors of 120 that are perfect squares. How about 4? 4 definitely goes into 120. So we can rewrite this as the square root of 4 times the square root of 30. The square root of 4 simplifies. That's great. That's 2. So we end up with 2 times the square root of 30. Now the square root of 30, it doesn't have any factors that are perfect squares. I know this for a fact. The factors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. None of those are perfect squares. What does this mean? It means that no matter what we do, if we factored this square root of 30 any further, we're not going to be able to simplify anymore. No matter what strategy we take, this is as far as we can factor it, and we can see that we can't simplify that at all. And so, when we're in this situation, we much prefer this as the simplified version of the square root of 120. While this is also, I guess, technically simplified, I mean, look at it. It's not very simple. We got a whole lot of stuff going on. So in that case, when factoring further doesn't lead to any more simplification, this is the form you want to leave your answer in. That is the simplified version of the square root of 120. All right, in these next two examples, we've got an integer out in front of this square root that we're trying to simplify. So for instance, this negative 5 in front of the square root of 40 might look a little menacing, but not at all. Just kind of keep that guy off to the side and deal with simplifying the square root of 40 while just continuing to copy down that negative 5 on each step. So let's see, factors of 40. How about 4? 4 is a perfect square and it's a factor of 40. So we can rewrite this as negative 5 times the square root of 4 times the square root of 10. All right, the square root of 4, that's nice, that's 2. And we have the square root of 10, and we end up with negative 10 times the square root of 10. So note, that negative 5, it just kind of hung out to the side there until we'd done our simplification, and then it showed up again. Same thing with 7 times the square root of 80. Let's keep that 7 there on the side while we try to simplify the square root of 80. Now, what are the factors of 80 that are perfect squares? I know 4 goes into 80, so maybe we can write this as 7 times the square root of 4 times the square root of 20. And that gives us 7 times 2 times the square root of 20, which is 14 times the square root of 20. Are we done? You know what? The square root of 20, I gotta believe we can do better than that. And let's see, factors of 20. 4 is a factor of 20. So we can write this as 14 times the square root of 4 times the square root of 5. The square root of 4 is 2, so 14 times 2 times the square root of 5. So 28 times the square root of 5. All right, and that's definitely our most simplified version. Now note, when you factor once and then you realize you kind of have to factor again, it means that there may have been a more efficient way of factoring in the first place. So in this example, if we had initially realized that 16 was a factor of 80, we could have done it a little quicker. But even if that doesn't pop to mind the first time you look at the problem, you'll still be fine. Now what about third roots? How do we simplify something like the third root of 54? Well, the strategy is going to be exactly the same. We're going to factor this into 2 third roots whose radicands multiply to 54. And now we want one of those radicands to be a perfect cube so that that third root will simplify nicely. So now we got to think, are there any perfect cubes that go into 54? 1, 8, 27, 27! 27 definitely goes into 54, and 27 is a perfect cube. So we can write this as the third root of 27 times the third root of 2, and the third root of 27, that's a very nice number, that's 3. So we can write this as 3 times the third root of 2, and this is the simplified version of the third root of 54. So you can see how similar these strategies are. Now we're just looking for factors that are perfect cubes, as opposed to factors that are perfect squares, like when we were simplifying square roots. All right, let's try 2 more. The third root of 40. Okay, now we got to think of factors of 40 that are perfect cubes. 1, 8, 8! 8's a factor of 40, and it's a perfect cube. So we can write this as the third root of 8 times the third root of 5. And the third root of 8, that's a nice number, that's 2. And we end up with 2 times the third root of 5, and that is the simplified version of the cubed root of 40. Last one. All right, that negative 6 out in front, don't worry about it. We're going to simplify the third root of 72, just keeping that negative 6 along for the ride. So we got to think, are there any perfect cubes that are factors of 72? 1, 8, 8. 8 again. 8 times 9 is 72. So we can write this as negative 6 times the third root of 8 times the third root of 9. And the third root of 8, that's a nice number, that's 2. So we got negative 6 times 2 times the third root of 9 for a grand total of negative 12 times the third root of 9. And that is the simplified version of negative 6 times the third root of 72. All right, time for some practice problems. So why don't you go ahead and pause the video and please simplify these 5 radical expressions, and when you're done, play the video and we'll see how you did. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.